In the previous class, we have discussed about the constant perturbation. Constant perturbation. So actually, it was time-regulated constant perturbation. That means, suppose perturbation is running in the range from 0 to T0. Okay. So in the graph, you can plot the effect of perturbation like that. It is T equal to 0, it is T equal to T naught. So the perturbation was on within this region, the perturbing region. And the effect of constant perturbation already we have discussed in the previous class. Specifically, we have discussed about the auto-ionization. The application of constant perturbation, which is an example of time-dependent perturbation, is auto-ionization. Auto-ionization in helium atom. So already we have discussed about this phenomenon, about this method or about this process in the previous class. Today we are going to discuss about another time-dependent perturbation, namely harmonic perturbation. Namely harmonic perturbation. So it is also a time-dependent perturbation, and the perturbing Hamiltonian, the perturbing potential, whatever you can say, this H prime is a harmonic function of time. So, for simplicity of calculation or for the advantage of calculation, I am choosing this is suppose H prime equals to twice V naught or twice V naught cos omega t. So it's an it's a form of harmonic perturbation with perturbing Hamiltonian like that. Omega is the perturbing frequency. Cos omega t. Omega is the perturbing frequency. So this is the expression or illustration of a perturbing Hamiltonian which is harmonically varying with time. H prime equals to twice V naught cos omega. You can find such perturbing Hamiltonian in case of a two-level system, and you are allowing an electromagnetic wave passing through the two-level system. Suppose you are allowing some electromagnetic wave having electric field E equals to E naught cos omega t, and magnetic field B equals to B naught cos omega t. And whenever any of these two, either electric field or magnetic field, be interacting with the atomic levels, then it can produce some potential energy which can act as a perturbing Hamiltonian, because you know the potential due to the interaction of electric field with some electric dipole is minus P dot E. So it will yield minus P naught cos omega t and some H factor. Suppose this is alpha. So you can say this P is proportional to cos omega t. So in such cases, you can find such time-dependent harmonic potential or time-dependent harmonic perturbing Hamiltonian. Okay. So, however, we are going to develop the general methodology or general tool to study such harmonic patterns. So, at first, we are going to regulate the perturbation with time. So, in a plot, suppose this is the time axis and it is t equal to 0 and this is t equal to suppose t naught, and we allow the system to be under the perturbation within this time range. So, here h prime x. Here the Hamiltonian is h naught, here the Hamiltonian is h naught, and here the Hamiltonian is h naught plus h. So h of t is equal to this one. So perturbation is acted on the system within this time range from t equal to 0 to t naught. And you know the effect of time dependent perturbation. Already we have discussed in several discussions. The effect of time dependent perturbing Hamiltonian or time dependent perturbation is the transition of the system. It will not change the stationary states or it will not change the spectrum. It only make the transition. It will transit the whole system from one initial state to the final state. And in some cases, you will find this transition from the initial state to a final state, which may be the part of a continuum state. And in the previous class, we have found such systems for constant perturbation. And here also, we can think of such transition. The transition from one initial state to a state which is final and which may be the part of continuum. So, we have to follow the Schrodinger equation from the perturbation expansion. The Schrodinger equation in first order correction of perturbation expansion is IH cut AF first order correction dot is equal to e to the power I EF minus EI T by H cut H prime of Fi, right, of AI naught AI naught, and it will be summation over R. Okay, it will be summation over R. Now we set up the system initially at the ith state. Suppose you have a system initially the wave function is I. So the system is initially at the ith energy level. That means AI naught is equal to 1. Okay, AI naught is equal to 1. Initially the system was in the ith level. Suppose so AI naught is equal to 1. And the other term, suppose I can use other index for convenience. This is suppose summation over j, and this is suppose aj. Yes. And the initially the system was in a particular state, which is say I state. I denotes for initial state. So the system was completely in the ith energy level. So AI naught is equal to 1, and the other coefficient, suppose AK or AJ is equal to 0 or J naught equals to 1. Aj naught is equal to 0 for j not equals to I, and aj not equals to 1 for I equal to j. That means ai not equals to 1. The system was completely in the ith level. So you can write aj naught is equal to chronic at delta j. Okay. So initially, because we have set up the system in such a way so that the system is completely in the ith energy. Now after transition, uh, it will make transition from the initial ith state to some final state, or the linear combination of the final states, which are the part of a continuum. Okay. So for this system, you can write IH card AF1 dot is equal to, we have only one options for J, which is AI, and AI dot is equal to 1. So, sorry, I have to modify this one also. So EJ, and this was also FJ. This was also FJ. Because summation over J it was. Extremely sorry for this one. But we have set the system which is initially at I set completely. So that's why I naught is 1. So for this particular case, you can write I cut f dot is equal to e to the power I ef minus ei t by h cut, okay, uh, h prime of fi into ai naught is equal to 1. Okay, ai naught is equal to 1. So that's why you can write ai dot, sorry, ai, sorry, f of 1, which will be minus I by h cut h prime of fi integration e to the power I f minus ei t by h cut into t. Okay, and after the perturbation was gone, so f1 at t naught, which will be from 0 to t. Okay, it will be, and the integration will be from 0 to t naught. Okay, another thing, because this h prime fi is the function of time, so the integration should be over the h prime fi also. So, okay, so integration from 0 to t naught h prime of fi. Okay. So now you can put the choice of h prime fi. H prime fi is twice v naught cos omega. Right? It's af1 of t naught is equals to minus 2I by h cut minus 2I by h cut t naught of fi integration from 0 to t naught into the power em minus ei t by h cut into cos of omega t dt. Very simple. Okay. Now let em minus ei is equal to h cut omega fi. Okay. Omega have the dimension of angular velocity from this combination. So let em minus ei be h cut of omega f. Then the equation can be simply written, which is af 1 of t naught is equal to minus 2I by h cut, then t naught of fi integration from 0 to t naught the power I omega t, sorry, e to the power I omega fi t and cos omega t dt. Okay, cos omega t dt. Okay, so now the question is, you have to solve this integration. You have to perform this integration. And in order to do that, you can write twice cos omega t is equal to e to the power I omega t plus e to the power minus I omega. Then you can split this integration in two parts. Okay, so you can write AF1 of E naught is minus twice I by h car T naught of A5. Then integration from 0 to T naught. Actually, you can drop this 2. Okay, so then drop this 2. Then you have charger switch the charger. Okay. So then you can write e to the power I omega f plus omega t by h cut. Sorry, omega f plus omega t plus e to the power I omega m minus omega of t. Okay. So of t. Okay. So from this one you can write fn1 of t naught. The integration will be 1 by I omega f plus omega, and the exponential term will be as usual. So you can write minus 1 by h cut t naught of f(i), then e to the power omega f(i) plus omega t naught minus 1. After putting the integration limit, you have omega f(i) plus omega, and then plus e to the power omega f(i) minus omega t naught minus 1 by omega f(i) minus 1. So we have found the transition coefficient, you can say, and the mod of the square of magnitude of this one will yield the transition probability. So the transition probability you can find precisely. Suppose this is t from I to f, it will be mod of at least up to first order. This is mod square. Okay, but here there is a twist, because if you look at here, if you look at the expression of this one, you can choose two different cases. Two different cases will dominate in this case. First one, if omega f(i) plus omega b 0 or tends to 0, you can say tends to 0, then this one will be very greater than the second term. So in the limit omega fi plus omega tends to 0, the first term will dominate. Okay, the first term will dominate. And in the second case, if you choose omega fi minus omega tends to 0, then the second term will definitely dominate over the first term. So instead of taking the direct effect of the transition probability, you can take the two dominant cases. Otherwise, in other cases, the contribution will be very insignificant. So the significant contribution to the transition probability will be from two different cases. First one, whenever this term will tends to 0, and the second one will be this one, omega fi minus omega tends to 0. Okay, so case one, uh, so case one, omega fi plus omega tends to 0. This means ef minus ei plus h cut omega tends to 0. Okay, then ef is equal to ei minus h cut omega. That means if ef less than ei, the final state energy eigenvalue is less than the initial energy eigenvalue. In this case, the first term will dominate. So generally, this can be corresponded to the emission, because the transition is from the higher energy level to the lower energy, which means it's emission. Okay. Whenever a particle, এবার বোর্ড দেখা যাচ্ছে?
হ্যাঁ স্যার।
ঠিক আছে। Okay, so in case one, whenever we have found the final energy level is less than the initial energy level, that means clearly it's an emission. So in this case, the first term will dominate. So let uh, primarily I am saying this is for the emission probability. Okay, so I am writing this is suppose omega or we. This is we. So we will be basically mod of that term square. Okay, mod of that term square. So that means phi of phi naught of fi by h cut mod square, and mod of e to the power I omega fi plus omega naught t by omega fi plus omega naught mod square. This was t naught minus 1. this is for emission whenever omega f less than omega. Similarly, in the other case, that means for omega fi minus omega tends to 0, which means em minus ei minus h cut omega tends to 0, or f tends to ei plus h cut omega, which is the final state energy eigenvalue is greater than the initial state energy eigenvalue, which correspond to which will correspond to the absorption of energy. Okay, you can think of the atomic energy level. An electron can absorb the energy and it will transit to the energy levels of higher energy eigenvalue. This is absorption. So whenever you have considered the case 2, which is really the absorption, then the second term will dominate, means this one, this term. So this one will correspond to the emission E, and this one will correspond to the absorption A. So obviously the transition probability for absorption, so I am writing this is WA, which is same on V naught Fi mod square by h cut square, and mod of e to the power I omega Fi plus omega naught, sorry, omega minus this E naught minus 1 mod square by omega Fi minus 1. So this is for absorption. Okay. So these are two dominant cases for this harmonic perturbation. One is for emission and another is for absorption. Okay. And you can calculate this emission transition probability and the absorption transition probability separately. And of course, this transition is from I to F. F is not a single discrete state. You have to consider this may be the part of a continuum state. So you have to incorporate all those of effects. So you have to transform. Suppose this is omega E. It will be integration of rho of EF of okay, okay. So you have to make the integration over all the continuum state or all the given range of the continuum state. So this is WE. Okay. So you have to write in that way, and then you can calculate all of this. So at first the emission. So this term e to the power I omega Fi plus omega E naught minus 1, and you can write e to the power I omega Fi plus omega E naught by 2, then it will be e to the power I omega Fi plus omega E naught by 2 minus e to the power I omega Fi plus omega E naught by 2. And mod of these one square will be mod of the whole term square, and essentially Mod of this one will be 1 because e to the power I theta and e to the power minus I theta will yield 1. And these two will yield twice I sine theta. So it will be 4 sine square omega fi plus omega t naught by 4 by 2, sorry. By, okay. Okay. So similarly, the minus case also. So this plus minus. So this will be plus minus plus minus plus minus. This will be plus minus. Okay. So in the expression of transition probability omega e, which will be function of t, it will be rho of ef. Okay, rho of ef. Then sine square. Okay, there may be some other constant terms which is 4h cut square v f dot square, whatever it may be. I am just dropping those terms. Suppose this was b. Okay, b into rho ef sine square of uh, omega plus omega fi e naught by 2 by omega plus omega f. Okay, this one of def. Okay. Now look at here. This is a sinc function sine square theta by theta, and it will rise at theta equals to 0. Any sinc function. Actually, this of theta square. Okay, because there was a mod of that square. Okay. So sine theta by theta, this function will raise up at theta equals to 0, and in the both side of this principal maxima, it will tend to 0. Okay, very negligible values. We have already found this function in diffraction pattern, in double slit diffraction pattern. Okay. So this whole integration term will blow up or will rise up very fast at theta equals to 0. So that's why you can say only the value of EF where this omega plus omega Fi equals to 0. That means EF will go to Ei minus H cut over. This value will only contribute to the integration. Okay, this value will only contribute to the integration, and the other values of EF will die because the contribution is very insignificant whenever the value of EF will deviate from this one. So in this case, you can write this WE of T naught. This is proportional to rho of EF, and EF tend to Ei minus H cut omega. And the other terms also, those are basically a time dependent term, which is dependent on T naught, and other constant terms. But the term which is very interesting is that the transition probability is very significant or very dominant whenever the final state will be initial state minus H cut. Okay, so this one. And you can make the similar calculation for the absorption also. This is for the emission. For the absorption, you will find omega Fi minus omega of T naught. So, of course, for absorption, omega T naught, it will be found that this is very proportional to rho of EF, and EF will be EI plus H cut omega. So the transition probability for harmonic perturbation, it is proportional to rho of EF, where final state will tend at EI minus H cut omega for emission and EI plus H cut omega for absorption. And these are the Fermi's golden rule. Fermi's golden rule for harmonic perturbation. Okay, so Fermi's golden rule for harmonic perturbation. This is E of T naught. This is rho of EI minus H cut omega, and absorption EI plus H cut. Okay, for constant perturbation, what was the form of Fermi's golden rule? For constant perturbation, what was the Fermi's golden rule? Pradeep?
Yes, sir.
What was the Fermi's golden rule for constant perturbation? For constant perturbation, the transition probability was in the order of rho of EF tends to EI. So this was energy preserving perturbation, because the only transitions were allowed which have the similar or nearing the initial state, energy nearing the initial state tends to, yes, EF tends to EI. So the final energy levels which are the part of continuum state, which are nearing the initial state, can be allowed in the constant perturbation. So that was the energy conserving perturbation. EF tends to EI. But harmonic perturbation, it is not the energy conserving perturbation, and the transition may happen from different energy eigenvalue levels, and we have found the Fermi's golden rule in that way for harmonic perturbation. No, this was not emission. This was actually it's found in autoionization. Constant perturbation was found in autoionization. Okay, and the examples of harmonic perturbation: the lasing action, That means the mechanism of a laser. So you can consider a two-level lasing system. One is initial level I and the final levels, which may be the part of a continuum state. So for simplicity of understanding, I am taking this as the F state. Okay. So case of absorption. In the case of absorption, if the transition is from I to F, so that EI is equal, EF is equal to EI plus H cut omega. Okay. So the gap of the initial and final state is H cut omega. Now suppose there is an electron here initially, and you allow some electromagnetic wave having frequency omega. So basically it's a photon of energy H cut omega, and this energy from the perturbation will be absorbed by the electron and the electron will jump up to the higher energy level F, and F has the energy Ei plus H current. So this is absorption. Okay, this is very trivial case. Okay, absorption of energy, and the electron will jump from the lower energy level to the higher energy level, and the energy gap was supplied by the external disturbances, which is termed as the perturbation. Okay, but the second term is very interesting. Second term is emission. Okay, second term is emission. So you know the normal emission. The normal emission is, suppose the electron is primarily here. The electron is primarily here, and uh, because the higher energy level has the lower average lifetime, so the tau is very low, then it will not be stable here. So it will emit energy and will make a transition to the lower energy level. And such type of emission is called the spontaneous emission. Spontaneous emission. What is spontaneous emission? The electron will make a spontaneous transition to the lower energy level, giving some electromagnetic wave or photon of energy h cut omega. And h cut omega is the gap of initial and final energy. This was an initial energy level Ei, and this is Ef. So Ef equal to Ei minus h cut omega. So it will yield the transition. It will yield the electromagnetic wave of energy h cut omega. Okay. So this is the spontaneous emission. There is no role of perturbation to the spontaneous emission. The electron will spontaneously emit. But here, in the case of the second term, okay, in the case of second term, the electron was initially here having energy Ei, and the system has another energy level Ef, which is Ef equals to Ei minus h cut omega. Now, if you allow some electromagnetic wave having energy h cut omega, due to the effect of this h cut omega, it will make a transition here, and it will yield another photon of energy h cut omega. Okay, so you allow the initial photon with energy h cut omega, and due to the perturbation of this photon, the system again will emit another photon having the same energy, and after that you will find the energy to be doubled, and in this process the amplitude of the photon can be amplified. Okay, and this process is the light amplification by stimulated emission, and this process is called the stimulated emission. And the stimulated emission is completely the harmonic perturbation effect. It cannot be explained from the normal quantum mechanics. You can explain the spontaneous emission from normal, the common quantum mechanics. But the stimulated emission, it's completely the perturbation effect. This emission happens under the effect of photon, which is a harmonic function of time. And due to the effect of this perturbation, the electron will make further transition to the lower energy level, which is emission. But this time, this emission is due to the effect of perturbation. And this perturbation or stimulated emission will yield the amplified light. Okay, the amplitude of the light will be doubled. Thus, this process is called the lasing action. You know the full form of laser, light amplification by stimulated emission of radiation. So, this lasing effect or the laser mechanism can be explained from the time dependent harmonic perturbation. So these are the two examples. These are the two examples of time dependent perturbation. In the previous class, we have discussed about the constant perturbation, which will correspond to the auto ionization. And in this class, we have discussed now about the harmonic perturbation, which will explain the latching effect or the latching action.